Well, thank you for the introduction. I'm Chiara CICCARELLI from Cambridge, and I'm presenting today a work that has been a collaboration between 4 different universities in the UK, although many of the authors, these affiliations are no longer updated. Some of the authors have moved elsewhere, probably as a result of Brexit. In particular, Koen Rock-Jeon, who did the work while he was a postdoc in Cambridge, has now moved to Halle, but also Matthias Eschrig has moved to Greifswald, if I'm not wrong. So the main purpose of this work was to investigate spin transfer into a traditional, conventional superconductor, niobium. Now, we didn't, without spending too many words on the introduction, many of the concepts have already been introduced by the previous speakers. Very briefly, singlet Cooper pairs are not good carriers of spin, and the reason is that they're in a singlet state. So ferromagnetism and superconductivity don't necessarily get very well along together. If we put a ferromagnet close to a superconductor, the exchange field of the ferromagnet tears the Cooper pairs apart and therefore leads to the closing of the superconducting gap at the interface. Now, if singlet Cooper pairs are not good carriers of spin, the same is not true for quasiparticles. For quasiparticles, it has been measured spin lifetimes exceeding those of normal metals, but also the spin diffusion length has been measured and to be above even the charge imbalance length scales, as in this experiment on the top right. So let's go now straight to the measurement. So in this experiment, we adopted a standard spintronic technique to inject spins into the superconductor, which is spin pumping. So the layout of the device that we used is shown on the top left here. We have a ferromagnetic layer, permalloy, 6 nanometers, sandwiched at the top and the bottom interface by a niobium layer, and then we cap everything with copper to slow down oxidation. Now, in spin pumping consists of exciting ferromagnetic resonance. To do that, we glue the sample upside down on a waveguide and transmitted microwave power through. So when the resonance conditions are met in the presence of an external field, the magnet starts to precess, generating a spin imbalance, and which then diffuses away from the ferromagnet into the environment. And as you see here in our layout structure, the environment is made by the niobium at both interfaces. Now here at the bottom right, I just want to point out that because the niobium is in contact with the permalloy, so we have the inverse proximity effect, which leads to a change in the superconducting transition temperature. And in particular, we explore different thicknesses of the niobium. For the thinner samples that we use, 7.5 nanometers, the sample doesn't even turn superconducting in the temperature range that we considered, which is from 2 Kelvin. Now, the measurement consisted in measuring the transmitted microwave power through the waveguide in a S12 configuration. When the resonance condition is met, microwave power is absorbed by the precessing ferromagnet, which then results into a resonance. So on this top graph, I showed the resonance as for a thickness of niobium of 30 nanometers, at different frequencies, which then corresponds to a resonance being measured at different magnetic fields. Now, a very important a key parameter in our experiment is the line width of these resonances, because the line width is directly related to the damping of the precessing magnetization. So the damping gives us an information on how quickly spin angular momentum is lost by the precessing magnet into the environment. Therefore, in this case, how quickly spin is transferred, how efficiently spin is transferred into the niobium. Now, but when talking about line width, we need to distinguish about 2 different sources of damping. The first one is the so-called inhomogeneous damping, which has to do with the presence of inhomogeneities, both in the sample and in the electromagnetic environment. But the damping that we're interested in is the viscous component of the damping, so which is parameterized by the Gilbert damping. And we can extract this parameter by plotting the line width of this resonance as a function of the microwave frequency, and extracting the gradient. The gradient directly gives us the Gilbert damping. So here I show different plots for different thicknesses of niobium and at different temperatures. Now, you see that in the higher thicknesses, like the 45 nanometers and the 60 nanometers, you immediately spot that there is a change in damping if we change the temperature. In particular, when we go to low temperature, when the niobium turns superconducting, the gradient of these lines decreases. So this immediately suggests that when the niobium turns superconducting, there is less spin angular momentum dissipation in the superconducting niobium. One other comment I want to make on these graphs is the fact that the inhomogeneous component of the damping, on the other hand, which is connected to the intersection of these lines with the y-axis, doesn't change significantly as a function of temperature. And therefore, this is just a comment to say that in some of the graphs here, for example, when I show the FMR line width instead of the Gilbert damping, the FMR line width gives us a direct indication on the trend of the damping. So I will not be making this comment for further measurements, but basically FMR line width is the same results would be applicable to Gilbert damping. So this graph here on the top left summarizes the results that I've shown previously, where we show the line width of the resonance as a function of temperature for different thicknesses. As you can see, the line width has an abrupt decrease when the niobium turns superconducting below the superconducting transition temperature, which is shown by the dotted line of the corresponding color. So this picture is in agreement. It's not very surprising, and it has indeed been observed also in the past by other groups, and it's in complete line with a picture in which quasi-particles are the carriers of spin in this case. So when we are above the superconducting temperature, the niobium behaves basically as a spin orbit coupled normal metal. So spin pumping is a standard. We can adopt a standard framework developed for normal metals to explain spin pumping into the niobium. Below the superconducting transition temperature, a gap opens in the density of states, which then hinders and limits the access to the quasi-particle states from the spins, and this leads to a suppression of the spin transfer. Now, as I said, this has been also observed in previous works in the past, which studied similar structures to what we studied with a permalloy film grown in contact with an niobium. And again, similarly, they observed a decrease in the damping in the FMR line width below TC. So to further remark the fact that this is, in this case, quasi-particles play the key role in spin pumping, we have fitted our results. For example, on this graph at the bottom right or the bottom left, we show the Gilbert damping as a function of niobium thickness for different temperatures. These results are completely fitted, where the fitting is the continuous line, by adopting the standard theory of spin pumping developed for normal metals based on the diffusive regime. Now, the only thing that we had to include in it is the opening of the gap in the density of states. Now, from the fitting, and the opening of the gap, I have to say, is gradual, and it is expected the gap is fully open within the depth of the niobium, within a length which is comparable to the coherence length of the Cooper pairs, which in niobium corresponds to about 15-16 nanometers. Now, from the fitting, we can also extract the spin diffusion length. And this further confirms that the quasi-particles are responsible here, because this spin diffusion length is correlated to a spin lifetime that is closer to the quasi-particle lifetimes before they decay into Cooper pairs by reflections, rather than being correlated to the intrinsic, to the natural spin lifetime that is determined by scattering and decoherence. So this further confirms that quasi-particles are indeed the carriers of spin. Now, so far so good, but something changes if we try to alter the device structure slightly. So in this second layout that we use for our experiments is identical to the previous one. So we have a permalloy layer sandwiched between two niobium layers, but then on the other side of the niobium, we put a platinum layer, 5 nanometers platinum layer. Now, the original purpose of having this platinum was to introduce an efficient spin sink that would have dissipated the spin angular momentum transfer through the niobium and would have allowed us to obtain a better estimate of the spin transport, a better understanding of the spin transport through the niobium. However, this modification of the out structure resulted in profoundly different results. So on the graph here on the left, you see again, in comparison to the previous results, the FMR, how the FMR line width changes as a function of temperature for different thicknesses of niobium. And differently from the previous case, for intermediate thicknesses of 15 and 30 nanometers, you see that instead of decreasing, the line width below TC increases, has an increase. So this seems to suggest that the spin transfer in the niobium is actually improved when it turns superconducting if platinum is present. Now, before I carry on with the analysis of these results and really try to understand what the mechanism is, I want to just open a small parenthesis on the effect of massless screening, because we know also that when the niobium turns superconducting, it deviates the electromagnetic, it expels the magnetic field, so it deviates the electromagnetic field lines and changes the electromagnetic environment in the permalloy, at the permalloy position. And this might be an issue. This has an effect on the FMR, and might have an effect on the FMR line width. So we need to take this, handle this with care. So what we observed is that in the devices that we use for our main analysis, where the niobium thickness is below the London penetration depth, which in niobium corresponds to about 100 nanometers, the effect of massless screening is irrelevant. However, if we have thicker niobium layers, like this one, 100 nanometers, comparable to the London penetration depth, then massless screening becomes an important effect that might lead to a misinterpretation of the results. So to show you here on this graph in the center, I show you the FMR line width as a function of temperature, as I did in the previous graphs. In this case, we see that below TC, the FMR line width increases despite we don't have any platinum present. However, if we now plot the two contributions of the damping, the inhomogeneous contribution and the Gilbert damping, we see that this is an artifact. The increase in the line width is an artifact due to the fact that the inhomogeneous damping increases below TC, while the Gilbert damping, which is the important parameter here, decreases as we would expect from a quasi-particle mediated spin pumping. Now, the reason why the inhomogeneous component increases so much below TC is which is also shown on this graph here at the bottom. So you see that the intersection increases dramatically with temperature. And the reason has to do with the rechanneling of the electromagnetic field lines due to the massless screening, which change the effective magnetic field in correspondence of the permalloy. And it did actually to plot this. So here in this graph at the center, at the bottom center, I plot the microwave frequency as a function of the resonance field for different temperatures. These graphs can be fitted by a Kittel formula, but we must take in order to obtain a good fitting, we must include an additional term to the effective field, which is only present again when the niobium is thick enough. However, in our case, we don't care about this effect. This effect is irrelevant. So we can keep talking about FMR line width safely. So an important graph which summarizes our results is the one on the bottom left here, which shows the ferromagnetic resonance line width as a function of niobium thickness at different temperatures. Now, for temperatures above TC, we see that, again, we fit the results by using the general theory developed for normal metals of spin pumping. The only difference with the previous case, when the platinum is present, the FMR line width increases for smaller thicknesses of the niobium, and this is because the spin conductivity of niobium is smaller with respect to that of platinum. So as we reduce the thickness of niobium, we have a more effective spin sink with the platinum present. However, things are unfitable by this theory below TC. So below TC, we see that we have a different behavior depending on the thickness of the niobium. So for thicknesses above 35 nanometers, we see that the line width decreases with decreasing temperature. But this behavior is completely inverted if we go to thicknesses below 30 nanometers, where we instead observe an increase in the line width with decreasing temperature. And the interesting aspect is that if you see the maximum line width that we measure for 30 nanometers, this is even larger than the extrapolated line width for zero niobium thickness when only platinum is present. So this results in just that superconducting niobium combined with platinum is an even better spin sink than platinum alone. On the top right, I show the change in line width measured as a function of niobium thickness, which gives us the magnitude of the effect, and the effect is maximum for a thickness of niobium of 30 nanometers, which corresponds to about twice the coherence length in niobium. Just a safety check on the bottom right, TC as a function measured for 3 different types of layers, of structures. Bare niobium is the black dots, then niobium with permalloy in contact with permalloy, with no platinum present is the red dots, and then the blue dots is when also platinum is grown on the opposite side of niobium. So we see that obviously when niobium is in contact with the permalloy, because of the inverse proximity effect, we see a rigid downward shift of the TC. But when platinum is then introduced, we don't observe any significant change in TC, and this means that the presence of platinum doesn't perturb the superconducting properties of niobium, as we would have expected, for example, if there is intermixing or anything that perturbs the nature of the interface. So now the main question that we asked ourselves is really, what is the role of platinum here? And to do that, we repeated the experiment with different materials and see what happened. So platinum, tungsten, tantalum, hafnium, iron manganese, copper, and we saw that this behavior of increasing line width with decreasing temperature was only observed in 3 cases, in the case of platinum, tungsten, and tantalum. Whereas for a light element like copper, we recovered the behavior of decreasing line width, therefore decreasing spin pumping for decreasing temperature. So this result already pointed towards the importance of the spin orbit coupling. I mean, we only see this effect when we have a heavy element present on the other side of the niobium. It was also interesting to do this experiment with iron manganese, which is an antiferromagnet, and which basically excluded that any role from quasi-particles. And the reason for that, so the mechanisms that we could think about that are triggered by quasi-particles but are still mediated by singlet Cooper pairs within the superconductor are cross-standard refractions and electron co-tunneling. So in these 2 effects, we have these 2 effects are started by quasi-particles at the 2 interfaces of a superconductor, which then coherently meet to to create a singlet Cooper pair, but these two effects then leads to a net spin transfer across from one interface to the other. So this could explain the spin propagation through the niobium to the platinum, and therefore a larger damping that we observe below TC. However, if these effects were actually true, then we would expect that they were enhanced when the quasi-particle density of states was larger at the interfaces with the superconductor. So in the case of iron manganese, because of the exchange field, again, we have an inverse proximity effect, which closes the superconducting gap at the interface. So we expect a higher density of states of quasi-particles. But instead, in this material, we don't observe any increase in the effect, rather a decrease. So this further confirms that quasi-particles don't play a role in our measurements. So, I mean, in the past, theory and experiment has explored the role of singlet of Cooper pairs in mediating spin transfer. So as we said, singlet Cooper pairs are inadequate to transfer spin, but what has been agreed by both experiment and theory is that when a superconductor is grown in contact to an exchange field, then spin-dependent scattering leads to a decoherence of the spin singlet state, which then leads to a non-zero projection to an S0 triplet state. So these triplet states are short range, and the reason is that they're still incompatible with exchange field. They're still torn apart by the exchange field within the ferromagnet and do not carry any spin. However, we can, once we generate these triplet states, then we can imagine to rotate them into a S1 triplet state. Again, where the S1 is with respect to the quantization axis, which is represented by the exchange field of the ferromagnet. If we can create these states, then these states are can propagate for much longer distances and are indeed in fact referred as long-range triplet correlations. Now, how do we rotate this? The general approach that the general approach that has been followed experimentally before the experiments that we did was to, instead of rotating the states, the triplet states, was to rotate the quantization axis. So basically, this occurs, for example, if the magnetization is not homogeneous at the interface between the ferromagnet and the superconductor. It's not homogeneous within the coherence length. In our case, this model doesn't apply because we have a homogeneous permalloy film grown in contact with the ferromagnet. We have no reason to believe that there are inhomogeneities to induce this rotation. But from the theory of Berger, we also have another possibility here. We have, if we have a homogeneous quantization axis, we have a homogeneous exchange field, we can always rotate the states around a spin orbit field. And this resonates with our measurements, where we have seen that the effect only in heavy spin orbit coupled material. So probably the spin orbit coupling here plays an important role. And this provided a first hint to our collaborators to develop a theory which is based in which two main elements are important, appear to be important for to explain our results. The first element is the spin-orbit coupling, as I said. So the superconductor must be in contact with a highly spin-orbit coupled material. The second element is the fact that this non-normal metal, this material, the platinum in this case, is close to a ferromagnetic transition, has a high spin susceptibility. So it is relatively easy to induce ferromagnetism. Now, based on these two elements, they have developed a theory. I'm not a theorist, so I'm not going too much into detail, based on the Wustadel equations, where with the introduction of the spin degrees of freedom. The key element is really the Landau parameter here. So in this graph here on the top right, I show how the spin currents depend on this parameter, where G equals to -1 corresponds to a paramagnetic transition. So you see that there is a peak up for a sufficiently high value of this Landau parameter. So if we can describe now the normal metal as a Landau Fermi liquid, then the presence of the superconductor leads to a superconductor proximity effect, for which the exchange field, an exchange field is induced within the normal metal and leads to a spin splitting. Now, the mutual presence of the exchange field and the spin-orbit coupling then gives us the two ingredients that we need in order to generate spin-1 triplet pairs. Now, in this graph here, it shows the trend, the calculated trend, and as a function of distance of the three states, the singlets, the S0 triplet states, and the S1 triplet states. As you can see, the triplet components constitutes a very small percentage with respect to the other two, but this is sufficient to pick up the main elements of our, the main features of our experimental results. In particular, at the bottom, the temperature dependence of the spin pumping, which increases with decreasing temperature, and the thickness dependence with respect to the niobium thickness. So the maximum spin transfer is expected for a thickness of niobium which corresponds to twice the coherence length, about 30 nanometers, as we indeed observe. So in order to really to pick up on this, to further explore the role of the exchange field within the platinum, now we decided to do a thought experiment to really intentionally increase this exchange field, internal exchange field. And the way to do it is to grow an additional layer, an iron layer in contact with the platinum, on the other side, in order to use an internal exchange field. I mean, previous measurements have shown this, that when the platinum is in contact with iron, for example, there is an induced magnetic moment because of the fact that of the high spin susceptibility of platinum, and this moment peaks at a thickness of about 1 nanometers. Obviously, when in this type of structure, when we have two different ferromagnetic layers, we have the iron and we have the niobium, we have the permalloy. So we need to be careful. When we do FMR experiments, there are two different resonances that we pick up due to these two layers. However, they are sufficiently distinguished and they have sufficiently different line width and features that we can extract the FMR contribution from the permalloy and carry the line width analysis that we did previously just on that. Again, some safety checks, in particular here. So at the bottom left, as you see, when iron is grown in contact with the platinum, we observe obviously a rigid increase of the magnetic moment of the material, but more importantly, the TC as a function of platinum thickness. You see that as the platinum thickness is reduced when iron is present in the structure, the TC decreases. And this is in agreement with an induced inverse proximity effect, the interface, and therefore a closure of the superconducting gap, because induced through the platinum because of the internal exchange field propagated from the iron layer. So these are the main results for this for the two different structures, one in which only platinum is present on the other side, and one in which we have this enhanced internal exchange field brought by the presence of the iron. So for in these two graphs, we plot the FMR line with as a function of platinum thickness, and above the TC, the two graphs show very similar trends. This can be fitted again by using a standard theory of spin pumping based on the diffusion model. And in both cases, the spin pumping saturates for the platinum thickness of between 2 and 3 nanometers, in agreement with the previous results of a spin diffusion length in this range. However, the results become very different if we consider temperatures below TC. So while in the first case, in the case where only platinum is present, the spin pumping saturates for a thickness of platinum as the thickness of platinum is increased, again for a thickness around 4 nanometers. In the second case, although we still have the same trend of increasing line with decreasing temperature, the maximum of the increase is then shifted towards lower thicknesses of platinum. So we see that a maximum increase in line width happens when platinum is in the range of 1.7 nanometers, which is very close to the thickness in which we are inducing the largest magnetic moment. So we have the largest exchange field and for the largest spin splitting within the platinum. So
the time is in principle over. So please.
Yeah, okay. So I'll go to the conclusion and skip this. Maybe if there are questions on this. So the conclusion is that we have measured spin pumping through a niobium layer, and we have observed a very efficient spin pumping when niobium is put in contact with a heavy element, such as paramagnets, such as platinum. And the maximum of the effect is for a thickness of niobium of 30 nanometers. And the effect is dependent on the internal exchange field of platinum. And I think I can just conclude here and point to you to the publications that resulted from this work. Thank you.